Okay, so welcome everybody to another webinar on compound extremes from the RiskCan compound events or compound extremes group. We still can't decide quite what to call ourselves after this many years, but there's so many terms floating around that maybe it's okay. And we have two very exciting talks today. One by Dirk Eilander, who's very well ensconced within the compound events community, talking about compound flood analysis from various sort of physical and risk dimensions. And then Cathryn Birch from the University of Leeds will talk about humid heat extremes over Africa. And as usual, we have our newsletters and our webpage and so on if you want to take a look at some of the community news and so on that we try to compile and send out for everyone's benefit. So with that, I will introduce Dirk. So Dirk Eilander is a postdoc at VU Amsterdam, and he's also a hydrologist at Deltares, which is a research institute. And as I mentioned, he's well integrated into the compound event scene and has been just about from the inception of it, including as one of the protagonists of our somewhat sister organization, which is called compoundevents.org. And his research and practice is in flood risk management, sort of from the technical, scientific sides, as well as the sort of consulting and collaboration with decision makers side. So his work is multifaceted, and I think we'll get a sense of that multifacetedness through his talk today. So very excited to have him, and I'll leave the floor to you, Dirk. Thanks for talking today.
Thanks for the introduction, Colin. I'll share my screen. So you should be able to see it now. Yeah, so today I'd like to present my work on the topic of compound flood risk modeling, and specifically about combining statistical, hydrodynamic, and impact modeling for compound flood risk. This work was done with a number of co-authors, but I'd like to specifically mention Anaïs, Philip, and Hessel, who have contributed to this research throughout my PhD journey, and it's also kind of a summary of the work I've done during this time. So I don't need to tell you probably all know how devastating floods can be. We just are reading the news now about the floods in Libya. But I made a slide just to give a snapshot of floods globally in 1 month at the time that I defended my PhD last November. At the time, there was widespread flooding in Pakistan, which lasted for months, affected 33 million people. And also in Nigeria, there were floods that lasted even longer. And those were two of the biggest floods at the time, but in many places globally, floods happened I found this just by looking at floodlist.com. So there might be even more floods going on in that month. And if we look at the drivers of these floods, many of them are caused by heavy rainfall. But also it's not always rainfall that falls locally, but also rainfall that accumulates upstream and then rivers flood. But also high downstream ocean water levels can cause these floods. And as you can see in this picture, also some floods are caused by multiple of these drivers, and those are the compound floods that I have focused on. So if you look at compound flood literature, you could broadly divide it into 3 categories. This is not very scientifically done, these categories, but with my gut feeling of following this literature. A lot of the literature is focusing on flood drivers. They assess the compound flood potential by looking at dependence between drivers or the co-occurrence of drivers in time. There's also research on more the hazard. That often includes hydrodynamic modeling, and then questions are answered like based on the simulated or highest water levels. What are the drivers of these floodings, these floods? And by combining those and also the impact of the consequences of these floods, people have also studied compound flood risk, although I think compared to the other categories, this one is a little bit less well developed still. And my work has mainly been on the flood hazard and flood risk analysis. So in the next slide, I will first show some work on the flood hazard and eventually on flood risk, and finish with some thoughts on ways forward in compound flood risk modeling. So at the start of my PhD journey, I first looked at compound flooding through a global lens, and developed this framework where we coupled a global ensemble of global hydrological models with a global tide and surge model, and then performed a continuous simulation continuous simulation to get water levels in delta regions that are the result of interactions between both downstream coastal and upstream riverine drivers. And based on this analysis, we could look at the extreme water levels in these deltas. We looked at over 3,000 deltas globally, the larger deltas, and classified the drivers of these extremes based on the rank correlations with between the annual maxima water levels and the associated water levels of the discharge and surge. And we found that about 20% of these locations could be classified as compound dominant. These locations generally have larger surge extremes or a very fast discharge response or a flat topography. So the faster discharge is in smaller catchments. We also found that larger catchments with a very flat delta also is prone to these compound interactions. And this highlights the importance of these compound floods. But it's too coarse really for any decision making. This is more type of study for awareness or agenda setting, let's say. So in the next research, we wanted to see how we could further develop this, get more understanding at a local scale, but still in a way that we could that would be globally applicable. So we could still do this at different places without too much effort. So we developed what we called a globally applicable compound flood hazard framework. So the idea here is that we still base our models a lot on global data set, but we basically simulate at a much finer resolution and more detail. So we can schematize the delta, the estuaries in more detail, and take into account the different boundary conditions. So for to make it globally applicable, not only the static data is based on global data sets, but also the boundary conditions come from global models. And using a package that I developed to set up models from data sets, set up hydrodynamic and hydrological models, which is called HydroMT. We are able to quite quickly set up these models, and we use a newly or recently developed fast hydrodynamic model called Sphinx to do the flood simulations. And we applied this to a case study in Mozambique, the Sofala province, where Beira is the capital. We looked at this flood event in 2019, tropical cyclone Idai, that hit the area and caused also quite devastating floods at the time. So for this region, using the approach I just discussed, we can set up this model. Here you see the topography and the different rivers. In this case, there is the Busi River flowing into the model domain at the west boundary, and at the north boundary, the Pungue River, and in the southeast, there is the Mozambique Channel, where the coastal water levels are the boundary to the model. So we account for all these different boundary conditions in this case. And we validated this for two events, so Cyclone Idai, which I just mentioned, but also Cyclone Eloise, which happened in exactly the same area about 2 years later. And this approach gives quite good results compared to similar large-scale flood models. And with this approach, we can now in much more detail look into how different flood drivers affect flooding. So here you see for those two events, a 2D map where dark colors indicate areas where water levels are higher because of the interaction between drivers compared to any single driver simulation. And also which drivers are dominant in which locations. The dark areas are often referred to as the transition zone between the different drivers. And you can see that for both events, these transition zones are quite different. That has, of course, to do with both the magnitude of the different drivers, but also the relative timing between the different drivers. So I think, to really understand compound flooding, we also need to look at a wide variety of plausible events. And that also brings me to the next part, which is on risk assessments. So here we want to combine the statistics with the hazard and possible consequences, the impact modeling, to come to flood risk as an aggregated measure of floods and consequences, often expressed as a monetary damage, an expected annual monetary damage, for instance, or people affected. And for univariate flood analysis, this is quite well established. But for multivariate flood risk analysis, this is still, I think, a field of research, how to best do this. So in our work, we developed this framework, where from the different flood drivers on the left, we simulate different combinations of all these flood drivers. That's, let's say, the workflow on the top, combinations of different return periods of those drivers, and then parallel assess the probability of those different combinations and combine that to calculate flood risk. So I'll walk you through how in this study we did those different steps. So first, the extreme value analysis. So for the different flood drivers, so in this case we had two rivers, coastal flood driver as well as fluvial flood drivers. We look at the extreme value statistic and derive for different return periods design events that we can use to force our model with. Now, one of the difficulties you then have with multivariate flood risk analysis is also how do you combine these drivers in time? We saw from the Idai and Eloise events that the timing between drivers also matters. So here we made a simplification by assuming a fixed time lag between the different flood drivers, which we based on autocorrelation between the different between the different drivers. So they're all relative to discharge in the Busi River. That's the river that flows in from the west, and we see that storm surge and rainfall in the area happens first. So those have negative time lag, and then water accumulates upstream and flows into the domain. And the discharge in the Pungwa, which is even a bit bigger river, is then enters the domain on average. And that's what we used for our hazard simulation. And for the impact simulation, what we do is to confront each of the hazard simulations. So in total, we ran 2,400 scenarios, looked at the exposure, buildings and populations in this case, and combined those together with the vulnerability that describes the relative damage based as a function of the flood depth. In this case, you get to an estimate of people affected or damage for a certain scenario. And parallel, we assess the multivariate probabilistics. Here we took an approach where we separated the co-occurrence and dependence modeling. So we made a distribution of how often which drivers co-occur in time within a certain time window, which is shown on the left. So on the top, you see a plot with over time how many different drivers co-occur in time. The dark blue events, which are 3, are events where all drivers occurred within a small time window. And then they're summarized in the histogram below. And on the right, you see the dependence between the annual maxima drivers. Here we took this assumption to base the dependence on annual maxima, as they often occur within the same wet season, and to have sufficient data points to fit this fine copula too. And then we combined both to create a stochastic event set of many thousand years of events, which show a variety of plausible events that can happen in this context. This was much inspired and co-developed with Anaïs and inspired by research she did for Ho Chi Minh City. Then to come to flood risk, we use this stochastic event set from the previous step and combine that with the impact from all those scenarios to get to a expected damage per year. And that results in the following risk curve. So now we can estimate the expected flood damage for different return periods and average annual expected flood damages. And we see that in blue, that is our estimates in case we assume there's independence between the different drivers. But if we account for the observed dependence, we see that especially for the more rare events, the damage increases about 12% for the 1 in 100 year event, for instance. So for this particular case, especially the rare events, which are the tropical cyclone events, have most, let's say, compounding effects. And this type of information, I think, is very relevant for decision making in that local context. But I already, so so some conclusions on compound flood hazard and risk modeling. In these deltas, this more integrated view of flood risk, I think, is important. We need to combine all these different facets of risk modeling, statistical hazard, and impact to come to a flood risk assessment. Both the dependence, co-occurrence, and time lags between flood drivers are important to account for in some way. And we have now also applied this framework to several other places, so it translates quite well to other locations. But there's still a number of remaining challenges. In the case I showed, we had 4 different drivers. But if we would account also for the time lags, for instance, in a probabilistic way, or we would have more drivers, the number of required simulations really explodes. So several approaches have been suggested to deal with this. For instance, to focus only on 4 simulations per return period, not simulate the all combinations of different return periods, but only simulate events that are important based on assumptions of the return of the response surface, let's say, so where the impact occurs and the probabilities. And also new methods are being developed to more adaptively sample events based, for instance, on meta models developed with artificial intelligence. So those could be way forwards to deal with this complexity. But at the same time, we also don't fully understand all the different pros and cons of the different approaches. As I explained, choices have to be made regarding the sampling strategies, also the timescales at which to look into the flood risk, and also many different dependence models have been proposed. And I think also, an important step forward is really to understand in which situations which approaches are valid and what bias they could introduce. One way also to simplify the complexity is to not try to do the multivariate statistics beforehand, where you need to take more assumptions, but simulate a large set of events and then look at the statistics of basically you reduce the problem to a one-dimensional problem again and perform the statistics on the outputs. But when you need a lot of very long time series to be able to do this. But also the differences between both methods, like what the pros and cons are, I think aren't fully explored yet. Future compound flood risk, how also flood drivers change with future climate, and also in relation with how the area will change, and therefore the flood response and exposure and vulnerability is a topic that still needs more research. And finally, delta regions are still quite data scarce as it comes to very important information for flood risks, such as bathymetry of the estuaries. And I think these flood risk assessments should also really move into the context of using them for flood reduction strategies to also give some that's basically what many decision makers are interested in. That's what I wanted to share. I'm not sure if there's time for questions now or later.
We can do a question or two right now if someone has one. Thanks very much, Dirk. That was really, really interesting here about how you're putting all the pieces together here. Does anyone have a quick question for Dirk?
Maybe we save questions to them.
Okay, yeah, if there's no quick questions, then
Yes,
we can
I
have
have
a
a
bit of a...
question.
Oh, sure. And can you introduce yourself also? Thanks.
Yes, I'm Maria. I'm a PhD as well, and I am studying the same topic of compound string event about rainfall and waves. And I wanted to know the dependency when you have multiple drivers. That is this case. How do you study the dependency?
Sorry, how do you study the?
Dependency. What statistical tool do you use? Copulas or any parameter or for correlation between drivers? How do you do it?
Yeah, thanks for your question. I went quite fast over that part, but in this case, we used a fine copula approach where we separated the modeling of the temporal aspect, the co-occurrence, and the dependence aspect in terms of magnitudes. But this is one of the approaches, as I explained also in later slides, that you could take, and definitely not the best approach in all cases. So there are, there's different literature out there, different approaches, and I think it's really important to start to understand when and where we should use which approaches.
Okay, but you do like between two drivers or between 2 and 2, or how do you do when you have several drivers?
So yeah, here we had multiple drivers, and they're not sampled conditionally. So by separating this temporal aspect and the magnitude aspect, we basically assess the dependence between joint annual maxima, which not necessarily occur at the same time, but so that's one sampling strategy, let's say.
Okay,
Yeah.
thank you very much.
Yeah, that's a good
Thank you.
question. There's always these little wrinkles that can be explored further. And obviously Dirk's thought about in putting this all together for his PhD and continuing research, and maybe it can be a conversation that continues later in the Q&A. But for right now, I'll turn it over to Cass to introduce Cathryn.
Great. Thanks. And thanks, Dirk, for your talk. So now we'll go over to Cathryn Birch. She's a professor in meteorology and climate at the University of Leeds. She has expertise in dynamical meteorology and high-resolution modelling of weather and climate, and works to better understand the causes of high-impact weather to improve weather forecasts, flood forecasts, and early warning system capability. Cathryn has previously worked at the Met Office and has recently commenced a project on humid heat extremes in the global tropics. And today she'll be talking about humid heat extremes over Africa. So over to you, Cathryn.
Thank you. Yeah, just share screen.
Can't see
There we
the
go.
slides.
Okay.
Oh, yeah.
You see that? Yeah. Okay. Oh yeah. So thanks, Cass, for the invite. So I'm going to talk about humid heat extremes over Africa, and this is work that I've done kind of on the side, I guess, of my main work, with the help of two of my postdocs, Lawrence and Sarah, and some collaborators at CEH in the UK and also at the Met Office. Okay, so what is heat stress? So heat stress occurs when the body's means of controlling its internal temperature starts to fail. Humid heat can be measured using something called wet bulb temperature, and that's essentially when what is measured by a thermometer, if you put some kind of cotton over the bulb and you wet it, and then when the air flows over it, it evaporates that water, and so you get a value of temperature which is lower than you do for dry bulb. But so the wetter the air, the less evaporation there is. So wet bulb is basically a measure of both humidity and temperature. And there's a limit to human survivability when the wet bulb gets high, because when it's really hot, you need to sweat, but then sweating's ineffective when the humidity is high. So because the sweat can't evaporate. So that threshold is between about 30 and 35 degrees wet bulb. So this is a really important question. There's been quite a few papers in the last 5 years which kind of try to characterize these heat waves and look at future projections of them. And the future projections are pretty grim. But what people haven't really done is looked at what the meteorological drivers of humid heat are in terms of the synoptic situation, what's going on at the surface, that kind of thing. So these papers are starting to come out, but it's still a kind of quite an understudied area. This is where I feel like my expertise of kind of tropical meteorology and dynamics kind of can come in to address some of this. So the aims of this study is firstly to understand the meteorological drivers of these events over Africa. So why have I chosen Africa? It's not the global hotspot at the moment of these events. In fact, the highest wet bulb temperatures are more over the Middle East and India and Southeast Asia. But Africa still has very high values, and the impacts on the populations there are likely to be very high, and also more so under climate change. And it's also, I know this region pretty well, I understand the meteorology, and I have model data available to look at this region. I'll also, because this is a compound kind of risk group, I'll also talk a little, had a little look at the kind of prevalence of humid heat flood compound events. So I'll talk about that, and I'll also assess the potential for early warning systems for humid heat. So the data that I've been using, so I've used a global atmospheric reanalysis called ERA5, and the reanalysis is basically our best representation of the state of the atmosphere, which we get by rerunning a global weather model with all available observations. And this is a really key tool over Africa, where we don't have a good high density of observations. So the reanalysis kind of fills the gaps. And then I also have a 10-year convection permitting climate model simulation for the present day, and then another one for the future, for the end of century. It's a high emission scenario. And these models are high resolution. They have a better representation of convection and moist processes than more traditional CNIP6 type climate models. So this is a useful tool where humidity is involved. So I'm doing this analysis over Africa. So there's different climatological zones in Africa. Over the equator, so this Gulf of Guinea region here and Central Africa is very humid and moist, and it's moist and rainy the whole year. And then further north and south, you have the more arid regions in South Africa and the Sahara Desert and Sahel. And then Africa sits, East Africa is somewhere between the middle, so it's equatorial, but it's a lot more arid than to the west. So I evaluate the heat wave at the heat waves over land only, and I'm looking at the daily maximum wet bulb temperature exceeding the 97th percentile for 3 or more days. So this is just a plot of the seasonality. So this is the median date of these wet bulb extremes, only looking at ones that get above 24 degrees Celsius wet bulb. And you can see it's actually, I was surprised how unnoisy this plot was, maybe. And there's some really obvious trends. So if you look over India, that these humid heat events are occurring in June over most of India. So this is not pre-monsoon hot dry bulb temperature events. It's separate to that. These are occurring later in the season, at the start of the monsoon season, where it's still quite hot, but also then you've got this influx of water vapor as well. And it's the same for the Sahel region of Africa. So here the events are happening in August, so it's during the monsoon season, so the wettest month of the year in that region, and it's kind of similar for Australia as well, sort of in December, January. So I looked at how much the drivers of these events differ in the different regions over Africa. So these plots show anomalies of some variables during these events relative to a climatology, so what the these relative to what these variables would you'd expect them to be usually. And there is some difference in behaviour. So if you look in the equatorial regions, in the moist equatorial regions, so Central Africa and Gulf of Guinea, so we'll just look at the purple bars to begin with. Here we do have a positive anomaly in dry bulb temperature. So dry bulb temperature is normal temperature. So this is a positive anomaly, and the humidity is also a positive anomaly. So both increases in temperature and that humidity are creating these events. You actually get kind of less cloud than you'd expect climatologically, which leads to more heating from the sun, and also more heating in the long wave, which is from the moisture in the air, and a kind of high evaporation. So that's that region. But then in the more arid regions, the north and the south, it is quite different. So if we look at the Sahel region as an example, which is the yellow bars, you've actually got this quite strong negative anomaly in dry bulbs in normal temperature, but a big not positive anomaly in specific humidity. So in these regions, it's the humidity that's driving these events, and you get during these events you get more cloud than you'd expect from normally, which actually reduces the amount that the sun's heating the surface, but all the warming is due to the water vapor in the air in the long wave, and you get an increased latent heat flux, which is evaporation from the surface. And then East Africa is somewhere in between, so that's on the equator, but it's a lot more arid, so it sort of behaves in between the two groups of regions. So evaporation is obviously important. So then I went on to look at rainfall. So these plots show the wet day anomalies during humid heat waves. So these are composite plots. So for all the events, I composite them. So day 0, so the first day of the heat wave, are all kind of composited on here. And the y-axis, the y-axis is the anomaly in wet days. So I've classified a wet day as more than 1 millimeters per day of rain, and this shows how likely it is that these events occur on a wet day relative to how likely wet days occur in the climatology. So if you just focus on the black line, which is from the reanalysis data, you can see the Gulf of Guinea and Central Africa along the equatorial belt actually have quite a small or even negative rainfall anomaly. So these events are not occurring more often on a wet day than wet days occur on average, because it rains most days in these regions. But further north and south in the more arid regions, you have these positive anomalies where humid heat extremes tend to occur on wet days much more frequently than the wet days occur in climatology. And it's not clear to me what the mechanism is there. Does the moisture come first, and then the rain come first and it evaporates from the surface and causes the near surface increase in wet bulb temperature, or is it actually the atmosphere is already really, really moist and wet already, and then that causes the rainfall? So we also looked at kind of what's going on with the synoptic circulation in these events. So for here, I've taken an example just for East Africa. So this shows the anomaly in 700 hectopascals, so that's the mid-level of the atmosphere, humidity, and also the geopotential height anomaly. So that shows kind of what direction the winds are going. So what we have during these events relative to how it normally is, we have this anomalous low pressure to the north here, which is driving these mid-level westerly winds. So it's basically drawing in this moist air from over the Congo region, from the equatorial moist region over East Africa. And that is basically driving increases in humidity. And also we're getting significantly positive precipitation anomalies. So it's raining more than you would expect on average. So basically what's happening is these events are occurring during kind of monsoon burst days. So it's during the monsoon period, and it's on the wettest days of these of the months with the monsoon in them. And then the next part is just to zoom in a little bit and just think about the sort of more local scale, and just to ask the question, within a large-scale humid heat event, where are people most at risk in this region? So we've got this large-scale advection of air from the west, which is humid, and we've got a lot of this rainfall, but where are actually the highest values? So the plot on the left just shows the orography height over Africa. So you can see it's actually quite mountainous. The yellow areas are high mountains, but you have these lower lying areas nearer the coast. So this plot here in the middle shows the maximum wet bulb temp. So sorry, this is just for a case study between the 1st and the 4th of April 2015. So it's not even a real case study. This is just from the climate model. So I just picked an example from the climate model. And this shows for over these 5 days, this plot shows the maximum wet bulb that's experienced at each grid box within this region. And you can see that it's high over the ocean, as you'd probably expect, because you've got a lot of evaporation over the ocean. There's also high values along the low-lying land near the coast, but then there's also high values further inland, and this is about 300 meters above sea level, and this is a really arid region generally, with very, very dry soil. You've got all these speckly values. Then it is a little bit different in the mean, so the mean wet bulb over the 5 days looks quite different. On average, the values are lower, but they're highest over the sea and also over the low-lying land near the coast. So this is a little animation of kind of what's going on. So this is hourly frames over the 5-day period. So the shading here is the temperature, and the arrows are the 10-meter winds, so the near surface winds. And you can kind of see there's just a lot going on at this kind of scale, and the wet bulb varies a lot regionally. So first of all, the winds are onshore for the whole period, although there is some variation through the day because of the land sea breeze. And you're getting advection of high wet bulb air from over the sea, and this is probably interacting with high sensible heat fluxes over land to create these kind of localized hotspots near the coast, which then are propagating onshore. But then also there's something else going on. So in the north here, in this box, you can see that kind of once a day you're getting these increased values, kind of quite speckly values. And this is basically caused by rainfall evaporating. So rain that fell either on the previous day or earlier in the day is re-evaporating to produce localized high wet bulb maxima. And that's just shown on this plot. So I've kind of zoomed in again, and I've taken the model data at each grid box in this little region. And I've plotted the daily maximum wet bulb temperature at each grid box versus the latent heat flux, so how much evaporation there is in the middle of the day. And you can see it's quite a strong positive correlation with the highest values occurring where the most evaporation is. And you can see that there are some values that were high at low evaporation, but we've looked at this and we think it's just areas along the boundaries of the wet soil which are being advected over the slightly drier soils. So what could an early warning system look like, particularly in arid regions? So this is just an example of the kind of thing that you could do. So at a kind of 2 to 7 day lead time, you could just very simply look at a global numerical weather prediction ensemble forecast model, and you could look at the synoptic situation and the advection of moisture, and you could come up with some sort of region, a prediction for a region which may be at risk of having a humid heat event. And then at a kind of shorter lead time, you could use a convective scale weather forecast, which will have a better representation of convection and rainfall, and it would have a better representation of things like the coastlines and the orography because it's high resolution, and you'll be able to get a kind of more specific prediction at the sort of more local scale of where people might be at risk. But then at even shorter lead times, so less than a day, or the kind of nowcast lead times, which are sort of 0 to 6 hours, you could use a combination of these things along with some observations of either land surface temperature anomaly from satellite, which is like a proxy for soil moisture, or some satellites measure soil moisture at the surface directly, or even satellite observations of rainfall to kind of get something that a kind of forecast at a very, very localized scale, perhaps even in more detail that's shown on my little schematic. Yeah, and then the last thing is just thinking very briefly about extremes. So asking the question, or compound extremes, so asking the question, how often might we get the co-occurrence of a flood and a humid heat extreme? So it could be that we know these events are quite often associated with rainfall. So how often is the rainfall at high enough intensity and a high enough accumulation to cause a flood? So it's kind of maybe you might get a lot of rainfall and a flood, and it might knock out the power infrastructure, and then people won't be able to run their air conditioning. So it's that kind of scenario. So it's hard to know where floods are. There's not a kind of nice gridded data set of where floods are over Africa at the moment. So to begin with, I've used just a very crude estimation of floods. So I've applied this weighted average of precipitation to my present day climate model simulation. And all it is it just smooths the mean precipitation, the daily mean precipitation, with some sort of decay factor, where after 40 days, the influence of previous precipitation on the surface is only 1%. And then you just assume that there's floods where this WAP is greater than the 95th percentile, and also the rainfall is greater than 10 millimeters per day. So I acknowledge it's crude, but it just gives you an idea of the kind of potential severity of the problem. So I've done that with the convective scale model. So these top two plots show the total number of days in 10 years where you get a same day, hot day and flood. So left-hand side, it just looks at dry bulb heat. And you can see there's very few kind of hot day flood events. They only occur in the southeast, but that's due to tropical cyclones in that area. Whereas with wet bulb heat, you get about, at the moment, present day, same day humid heat and flood maybe occurs 1 or 2 times per day in the present day. And then if you look at the future change at the end of century, using RCP 8.5, you can see you get large increases both with the compound events for dry bulb and for wet bulb heat. But if you look at the difference in the future change, which is the plot on the right, you can see the change is larger for the humid heat events. So at the end of century, it's perhaps up to 20 days per year. You might be expecting this kind of compound event, bearing in mind the limitations of the methodology. So in summary, so humid heat extremes are generally driven by moisture transport, cloud, long wave heating, rainfall and evapotranspiration in most parts of Africa. Although shortwave is a factor in the equatorial regions that are already very humid. There is this possible humid heat flood compound extreme. It may not occur that much in the present day, but it will almost certainly increase in the future. On the local scale, humid heat maxima, in the example I showed, occur near the coast over low-lying land, when air is evected over from the sea, and also over regions with high evaporation from previous rainfall. And for these arid regions, there is a possibility of developing an early warning system based on NWP data and satellite observed soil moisture. And just a final thing, so I guess this talk, most of the work in this I've kind of just been doing on the side. I have got a project funded on this now called Humid Heat Extremes in the Global Subtropics. So this is a £1 million project. It's for 3 years. It's just started. It's with colleagues in Leeds and at the Centre for Ecology and Hydrology, and we'll have 2 postdocs and 2 PhD students working on all of the questions that I brought up in this talk. So specifically looking at the atmospheric and surface drivers of humid heat extremes across the global tropics and subtropics, looking a bit at the compound heat and flood extremes, and then thinking specifically about this predictability on weather forecasting timescales, with a view of developing early warning systems. And we'll also do some climate risk mapping of these kind of localized hotspots. So I have quite a few partners already. So they're a number of the national Met services across the tropics and also in the UK. But I'm keen to grow that group. So if anyone wants to be involved, please get in touch. And that is everything.
Great, thanks, Cathryn.